Okay, so we're going to move ahead to section 11-3, which deals with the P-series test and the integral test. And I think from like an algebraic standpoint, I think P-series test is probably the easiest, most efficient test for us to use to determine convergence or divergence. And I think integral test is might be the most like algebraically complicated test to use. So we're going to take a look at both of these. So these are tests 4 and 5, respectively, to test for convergence or divergence of a series. So P-series test, which is test number 4, says given the sum from n is equal to 1 to infinity of some formula 1 over n raised to the p power, if your exponent p is larger than 1, the series converges. And if the exponent p is less than or equal to 1, the series diverges. Okay, so really easy test there to utilize. Okay, and then test number 5, the integral test, says to suppose that the function f is a continuous, positive, and decreasing function on the half closed interval from k to infinity, and we're going to let a sub n be equal to f of n. Then the first part says that the sum from n is equal to k to infinity of a sub n converges if and only if the integral from k to infinity of f of x, which we are integrating with respect to x, converges. Okay, so with one of our limits of integration, in this case the upper limit of integration being infinite, we're going to have to use the limit definition for improper integrals to evaluate that integral. All right, and statement number 2 says if the sum from n is equal to k to infinity of a sub n, that is going to diverge if and only if the integral from k to infinity of f of x, which we are integrating with respect to x, diverges. Okay, so we'll take a look at a few examples of both the P-series test and the integral test. Okay, so these directions here for these examples ask us to determine whether the following series converge or diverge. Now, the two tests that we looked at in the previous section, the nth partial sum test and the geometric series test, those tests are unique in that if we had a convergent series, we could find the sum of the series. We're not going to be able to do that for these two tests or subsequent tests as well. Okay, so we're only going to be able to determine convergence or divergence, not what the value of the sum is going to be equal to. Okay, so for number 1, we have the sum from n is equal to 1 to infinity of 4 divided by n. Now, if we want to do this the quickest and most efficient way, this is a candidate for the P-series test because I can rewrite this pulling the factor 4 out front. So this is going to be 4 times the sum from n is equal to 1 to infinity of 1 over n. So this is like 1 over n to the first power. And because our exponent is less than or equal to 1, this series here is going to diverge. So it diverges by, I'm going to abbreviate the P-series test as PST. If you want to write that the exponent 1 is greater than, or sorry, is less than or equal to 1, as like your proof that it diverges, that's perfectly fine for you to do so. Okay. Okay, let's do this the other way, because this is one that we can show utilizing the integral test as well, although that would be a really poor choice because it's a lot more algebraically intensive for us to figure that out. Okay, so what we're going to do here if we want to use the integral test is we're going to rewrite the function f of x as the formula for our series, but written in terms of x instead of n. So I'm going to rewrite this as f of x equal to 4 divided by x. And then our function has 3 criteria that it has to meet in order for us to be able to in order for us to use the integral test. So first criteria is that f is continuous. So it has to be continuous on the interval from 1 to infinity. And if we check the domain of our function, the only spot that our function is not continuous is that x is equal to 0. So x can't be equal to 0. But the function is defined everywhere on that half-closed interval from 1 to infinity, thereby making it continuous on that interval. Okay, next. So condition number 2 is that f is positive. Okay, so as long as we're plugging values, natural numbers between 1 and infinity, 4 over x is going to be a positive quantity, so that checks out as well. And then the third criteria is that f is decreasing. Okay, so real quick way for me to check to see if f is decreasing is I'm going to take the derivative of this function, and the derivative of this function becomes negative 4 over x squared, and that is going to be less than 0 on the interval from 1 to infinity. So that criteria checks out as well. Okay, so what we're going to do then is we're going to take the integral from 1 to infinity of 4 over x, which we are integrating with respect to x. Again, because my upper limit of integration is infinite, I'm going to rewrite that using the limit definition of an improper integral. So I'm going to rewrite this as the limit as t goes to infinity of the integral from 1 to t of 4 over x, which we are integrating with respect to x. Antiderivative of that is going to be 4 times the natural log of the absolute value of x, which we're going to evaluate at t and at 1. So this becomes the limit as t goes to infinity of 4 times the natural log of the absolute value of t. Since we're taking the limit as t goes to infinity, I don't need that quantity inside of absolute value bars. Minus 4 times the natural log of 1. We know the natural log of 1 is 0, so that quantity goes away. And as t gets large, 4 times the natural log of t goes to infinity. Okay, so because the integral diverges, therefore the series diverges by, and then I'm going to abbreviate the integral test as IT. Okay, so we have the ability to both use the p-series test and the integral test in this particular case. It's just the integral test is by far the worst choice. Okay, it's significantly more work than the p-series test is in this case. Okay, so let's move on to number 2. So for number 2, we have the sum from 2 to infinity of 1 over n times the natural log of n. Okay, so again, integral test is going to be the test that we want to use. Hopefully you can tell looking at that formula that that's going to be a good candidate for u substitution as far as integrating that goes. Okay, so we want to check to make sure that our function satisfies the 3 conditions. Number 1 is that f is continuous. And again, we're checking this all on the interval from 2 to infinity. So the only values that are not going to be in the domain of that formula are n is equal to 0 and n is equal to 1, because both of those values make your denominator 0. F is defined everywhere on the half-closed interval from 2 to infinity, thereby making it continuous on that interval. Okay, next is that f is positive. Okay, so when I plug values of 2 or larger into that formula, both the numerator and denominator are going to be positive, so that resulting quotient will be positive. And then criteria number 3 is that f is decreasing. So what I'm going to do is differentiate that formula. So if that formula, f of n, like I can rewrite that as n times the natural log of n raised to the negative 1 power. So when I differentiate that, f prime of n, that'll be negative 1 times n times the natural log of n raised to the negative 2 power. And then using chain rule, I have to multiply by the derivative of the inner function, which I have to use product rule to differentiate. So that's the derivative of the first, 1 times the second, the natural log of n, plus the first n times the derivative of the second, which is 1 over n. So I can rewrite f prime of n as the natural log of n plus 1. I'm taking the opposite of that whole thing and then dividing it by n times the natural log of n squared. And as long as I am picking values 2 or larger to plug in the place of n, that is going to be a negative quantity. Okay, so f is going to be decreasing. It satisfies all 3 of those conditions, which means it's a candidate to use the integral test to determine convergence or divergence. Okay, so what we're going to do here is we're going to take the integral from 2 to infinity of 1 over x times the natural log of x, which I'm integrating with respect to x. Again, our upper limit of integration is infinity, so we're going to rewrite that using the improper integral limit definition. So I'm going to rewrite this as the limit as t goes to infinity of the integral from 2 to t of 1 over x times the natural log of x, which I'm integrating with respect to x. I'm going to do a u substitution to evaluate this integral. So I'm going to let u equal the natural log of x, which makes du equal to 1 over x dx. So I can rewrite this then as the limit as t goes to infinity. I'm going to rewrite both limits of integration in terms of u values. So the lower limit will be the natural log of 2. Upper limit is going to be the natural log of t. I can rewrite that formula doing the u substitution as 1 over u du. And then I can evaluate that integral by taking the antiderivative. So that's the natural log of the absolute value of u, which we're going to evaluate at the natural log of t and the natural log of 2. So this becomes the limit as t goes to infinity of the natural log of t. I don't need the natural log of t inside of absolute value bars because as t gets big, the natural log of t is going to be a positive quantity minus the natural log of the natural log of 2. Okay, and the natural log of 2 is also a positive quantity. Okay, so as t gets large, the natural log of t gets big, and the natural log of something going to infinity, that goes to infinity, which means that the integral diverges, so therefore the series diverges by the integral test. Okay, so I want you guys to try this third example. Go ahead and pause the video to do that, and then I'll go ahead and work it through after you are done. Okay, so for number 3, we have the sum from n is equal to 1 to infinity of n times e raised to the negative n squared power. Again, this formula here is one that we are going to be able to integrate by u substitution. So let's check and see if this is a candidate to use the integral test on. Okay, so again, our 3 conditions are that f is continuous, f is positive, and f is decreasing. And we're checking all of these on the half closed interval from 1 to infinity. Okay, so we can think of this formula here as being n over e to the n squared power. And that function is going to be defined everywhere, thereby making it defined on the interval from 1 to infinity, thereby making the function continuous on that interval. Okay, as long as we are plugging values in between 1 and infinity into that function, both the numerator and denominator are going to be positive. So that resulting quotient is going to be positive. Okay, and then let's check the decreasing part next. So I'm going to differentiate this. So f prime of n using product rule in conjunction with chain rule. That will be the derivative of the first, which is 1 times the second, e raised to the negative n squared power, plus the first, n, times the derivative of the second, which is e to the negative n squared power, times the derivative of the exponent negative 2n. So when I go through and simplify this, I'm going to go ahead and factor out e to the negative n squared power. When I do so, that leaves me with 1 minus 2n squared. Okay, so I want to determine critical points for this. E to the negative n squared power, that's never going to be 0. 1 minus 2n squared, the only critical point for that on the interval from 1 to infinity will be when 2n squared is equal to 1. That happens when n squared is 1/2, and that happens when n is positive rad 2 over 2. It also has a critical point at negative rad 2 over 2, but that does not lie on the interval from 1 to infinity. Okay, so our only critical point we have to test is rad 2 over 2. And when I make a sign chart for that, if I pick a value bigger than negative rad 2 over 2, that derivative's value is going to be negative, which means that that function is decreasing. Okay, so all 3 conditions are satisfied, which means this is a candidate for the integral test. Okay, so let's go through and determine convergence or divergence utilizing the integral test. So I'm just going to jump right into the limit definition here. So I'm going to take the limit as t goes to infinity of the integral from 1 to t of x times e raised to the negative x squared power, which we're integrating with respect to x. I'm going to do a u substitution where I let u equal negative x squared, which makes du equal to negative 2x dx, and dx equal to du over negative 2x. So this is going to become the limit as t goes to infinity. I can pull negative 1/2 out front. I'm going to rewrite both limits of integration in terms of u values. So upper limit is going to be negative t squared. Lower limit is going to be negative 1. And then the function that I'm integrating is e to the u power, which we are integrating with respect to u. Okay, so when I take the antiderivative here, we get negative 1/2 times e to the u power, which we're going to evaluate at negative t squared and negative 1. So this becomes the limit as t goes to infinity. I'm going to pull negative 1/2 out front, we get e to the negative t squared power minus e raised to the negative 1 power. So I can think of this as the limit as t goes to infinity of negative 1/2 times 1 over e to the t squared power minus 1 over e. As t goes to infinity, the denominator, e to the t squared, goes to infinity, so 1 over e to the t squared goes to 0. So this winds up becoming 1 over 2e, which is a finite number, which means that the integral converges, and if the integral converges, the series converges. By the integral test. Okay, so again, it's a pretty involved process, like showing an integral converges or diverges by the integral test. So for me personally, when I'm doing these problems, I try to avoid using the integral test if I have the ability to do so, which you're not always going to be able to do with these problems. Okay, last example, we have the sum from n is equal to 1 to infinity of 3 minus 2 rad n over n cubed. And I'm going to do a little bit of algebraic manipulation to this. So I can rewrite this as the sum from 1 to infinity. I'm going to take that quotient and split it up into 2 fractions. And then I'm going to take the sum of each of those fractions. So the first fraction, I can take the numerator 3 and divide it by n cubed. And then I'm going to subtract the sum from 1 to infinity of 2 rad n over n cubed. So 2 rad n over n cubed is like 2 times n to the 1/2 power minus 3rd power. Because again, when we divide two exponents that share the same base, we subtract their powers. 1/2 minus 3 is negative 5/2. So I can rewrite that quantity as 2 over n to the 5/2 power. Okay, so when I do that, I can rewrite that first sum as 3 times the sum from n is equal to 1 to infinity of 1 over n cubed. We know that that converges by the p-series test minus, I can pull 2 out front and rewrite that as the sum from 1 to infinity of 1 over n raised to the 5/2 power. That also converges by the p-series test. So if both of those series converge by the p-series test, the difference converges by the p-series test. Okay, so that's it. That'll wrap up section 11-3. Pretty short section. I think 11-4, we start like having the ability to work with more slightly more complicated series in the next section, where we look at the comparison test and the limit comparison test. Okay, so that's it for today. Hope you guys have a great rest of your day.